Good afternoon, everybody. Just wanted to welcome everybody to our webinar today. I'm going to just kind of introduce our speaker in just a moment. Just wanted to go through a couple of housekeeping items. While we're doing the presentation, we do have everybody's lines muted, just so we don't get any background noise to distract from the presentation materials. We will be able to take questions. We can do that in a couple of ways. If you do have questions during the presentation, feel free to use our chat or our questions function in the panel there, and we can interrupt if there's a really pertinent question that's kind of relevant to what we're talking about at the time. We'll kind of stop and we can ask David, our speaker, to possibly mention that. We'll also have time at the end to take some questions as well. Before we get started, I've already mentioned that our speaker's name today. So we've got David Layzell, who is the co-founder and research director with the Transition Accelerator and the executive director of the Canadian Energy Systems Analysis Research body, so CESAR. He began his academic career as a professor of biology at Queen's University and generated an international reputation. He was elected as a fellow of the Royal Society of Canada. Over the 20 past years, his interdisciplinary research efforts have focused on exploring and defining transition pathways capable of moving Canada to a more sustainable future. His work has led directly to the activities of the Transition Accelerator to build out a hydrogen economy across Canada, which is, of course, what he's going to be talking about today. So without any further ado, we're going to hand this over to David. And like I said, if there's any questions that come up, do feel free to use the chat function while everybody's muted, and we'll be unmuting people at the end and also still using the chat at the end to answer questions. So David, we'll hand it over to you.
Well, thank you very much. It's a real pleasure to be able to talk to everyone today, and I appreciate people taking time out of their busy days to come and listen to this presentation. I'd like to start by just recognizing all my collaborators on the right-hand side, and Dan Wickham as well, who's the CEO of the Transition Accelerator. So in the talk today, what I would like to do is to really cover three things in the outline. To talk very briefly about the net zero challenge that Canada is committed to, and many companies have committed to across Canada, and provinces have committed to as well. And then talk about the Transition Accelerator, which is a new not-for-profit, and then talk about the work that we've been doing with the Transition Accelerator and as part of CESAR to build out transition pathways to a hydrogen economy across Canada that can really help to address economic issues as well as environmental issues. Net zero emissions, as you can see on this chart, we see the actual emissions in Canada are in red at the top here, and the past commitments that we've made, the Kyoto commitment, the Copenhagen commitment, the Paris commitments, it's pretty clear we haven't done very well in actually achieving those commitments, although we have turned the curve on our emissions from continuously rising. Canada has recently, and at least 15 other countries of the world have recently committed to be net zero by 2050. So to drop their emissions by in the next 30 years to have the emissions decline to net 50. This challenge, you can see the steepness of these slopes compared to the past commitments are much more challenging. But it is actually valuable to have a net zero target, because it really forces you to actually think about the transformation of systems rather than thinking just about incremental change. And of course, this changes when they talk about net zero. It could include emission reductions, certainly large emission reductions from our human systems of transportation, space heating, industrial processes, etc. But it also could include carbon removal technologies like afforestation and either some technology for pulling CO2 out of the air. Transformational changes are going to be needed in order to achieve a net zero emissions. So what we've been looking at in CESAR and in the Transition Accelerators is how do we get there, and what does a net zero Canada look like, and how can Canada win and do it in terms of international global competitiveness. So the Transition Accelerator is an organization that I've been involved in helping to set up over the last year or so. It's a new pan-Canadian not-for-profit charitable organization. It's been established with the encouragement and support of a number of philanthropic foundations across Canada that has some of those that were funding my work before, and we talked about trying to expand their activities. So we set up the Transition Accelerator. It's headquartered in Alberta, and Dan Wicklum, shown here, is the president and CEO. And its mandate is really to accelerate systems level transitions of sectors in Canada to address major societal and business challenges. So it's not only about transitions to transform our energy system and transform our fuels for non-emitting. It's actually about transforming systems to make them more efficient, more compelling, more economically viable. So it's actually about a larger transformative systems change where greenhouse gas solutions are actually built into the solutions. Greenhouse gas reductions are built into the solutions. The philosophy, and if anybody wants a cure for insomnia, there's a report that we wrote and released in August of 2019 that talks about the philosophy and the theory of transition theory and about how what we are doing here would work and what our philosophy is on this approach. It starts by really having a deep understanding of the systems we want to change and understanding also that we live in a time of transformative disruptive change, and some of those changes that are happening today can either be good or bad. So what we want to do is to harness the technology, business model, and social innovations that are already at play in society that usually targeted at new business models and societal objectives, and want to make sure that we embed within those greenhouse gas reduction targets. And so part of the things we do within the accelerator is do a lot of techno-economic and environmental assessments, but also look at the policy environment and engage the industry to try to influence policy and investment decisions to really build industry-led consortia that are going to direct the disruptive forces that are already at play that achieve societal goals that include climate change. So it's worth quoting this Nobel Prize winner from 50 years ago that, we can't really predict the future, but maybe we can invent it. And we're trying to invent a better future for Canada. The approach that we use in the methodology is to deep understanding of the systems that we're trying to change, whatever that system is, and usually is by sector, but understanding the compelling drivers that are already at action. What are the technology, business model, policy, and social innovations that are actually impacting that sector? And then we engage with the companies and the innovative companies, the coalition of the willing, if you like, as well as academics, government, and others to develop a shared vision for the future of that pathway. We do a lot of modeling and analysis of that to try to make the pathways plans more credible, compelling, and more capable of achieving the goal. And then the item 4 over here, this is a highly interactive process in the middle here, but we start spinning out consortia-led projects that will actually put us on the journey, if you like, to a low carbon or net zero Canada. So when we talk about transition pathways, which is really what we're trying to define, it's really the sequence of actions, the technology deployments, what investments, what policies, et cetera, are needed to achieve a desired endpoint. And the pathways differ for regions and sectors across Canada. What we are trying to do in Alberta may be related to something that's similar to Ontario or Quebec or other provinces, but there's the approach of how you would do it is going to be different, and we're finding that is a really important feature of our initiative. The accelerator is really looking at 4 things in different parts of Canada. A study on cross-border electricity trade, really focused on Quebec in the northeast. Autonomous vehicles on demand is another one, sort of on mobility as a service and how it's going to disrupt the personal mobility sector. And so how do we direct it in a way which is positive to society and environment? And the agri-food sector, interest in that. And the hydrogen economy with a particular focus on freight, but actually it's broader than that, as you'll see from the discussions today. So I'm going to be only talking about the last one on the hydrogen economy. So what we want to do is the rest of my talk is really focused on how the work we've been doing to try to build out transition pathways to a hydrogen economy. And to understand that, we actually really need to understand our existing energy system and what are the problems with it from a climate change perspective. And what we've done, what I've tried to represent here is some a diagram of the more or less the structure of the energy systems in Canada today. And in reality, we have three energy systems that operate in Canada. One is a thermochemical system, which is really provides everything from space heating and water heating in our homes and other commercial buildings, etc. It's also all the heat for industrial processes and the reductant in terms of, for steel making, and so the energy and thermochemical energy that goes in to make steel or fertilizer, etc. Right? So those are the thermochemical processes. Most of the energy comes from coal, from natural gas, and from bio in the pulp and paper sector, for example. There's another sector here, which is really about light, computing, cooling. And it's only really the only fuel for that is electricity, and it's provided, of course, the electricity is provided in Canada. This is the Canadian mix, a lot of hydro and nuclear, but in places like Alberta, we have coal and natural gas providing a significant portion of our electricity. And then, of course, we have the transport sector, and where most of the energy comes from gasoline and diesel. Now, if we're going to move to a net zero energy system, it's very clear that what we need to do is to stop producing greenhouse gas emissions from distributed end-use fuels, from the tailpipes of our cars, from the chimneys of our houses. You just can't possibly get to net zero if we continue to combust carbon fuels in those locations. We could replace those with low carbon electricity. That's a possibility. And indeed, that's probably the more economic if you can do it, if you can make it fit. But there are many of the end-use energy demands where electricity just isn't a very good choice. And the other possibility, of course, is look at zero-emission fuel or hydrogen, that if that better fits the demand. And we also need to dramatically reduce the emissions from the production of the fuel and power. So it's these emissions that we're showing out here also have to be reduced. And eventually, we're probably going to still have some emissions left just because of the nature of the system in 30 years. So we're going to need to use negative emission technologies to get to net zero. Now, what I guess we're looking at in the study that I want to talk about today is our focus is on the hydrogen piece. The zero emission fuel hydrogen, and see how we can actually produce it, because we already have an electrical grid. It's got its own challenges, but the hydrogen is a big challenge. It's something that we don't really have as part of our energy system today. Now, when you look at the three energy systems that I was just describing here, the thermochemical, transport, and we pay a very different price for each of those energy fuels. And so I put all of these on the basis of dollars per gigajoule. For heat, we tend to pay only, $2 to $10 a gigajoule for heat. This is, if you're an industrial user, you might get it as cheap as $2, especially in Western Canada, then up to maybe $10 or maybe $12 if you're really paying a high price. But we don't pay very much for heat. For electricity, we pay more. If you're talking $50 to $100 a megawatt hour, is $14 to $28 a gigajoule in this same units as heat. So we pay 2 or 3 times the price for electricity as we do for heat. For transportation, we basically pay twice the price that we pay for electricity, in the range of $25 to $38 a gigajoule. So that's 90 cents a liter to $1.30 a liter. So our focus is looking at hydrogen. We're really starting to focus on the transportation sector, because the high value of that sector is an easier target for alternatives like a hydrogen to act on. So that's the focus. And indeed, Alberta and Canada have been recognized internationally as among the lowest cost producers of carbon-free hydrogen. This is a Japanese study published in 2018. If anybody wants to go to it, I'll make these slides available. There's the link there. And the Japanese have identified Canada as producing hydrogen from natural gas coupled to carbon capture and storage. When they assumed a natural gas cost of $4.27 Canadian a gigajoule, they came up with about $10 Canadian. I've converted these values from US dollars, et cetera, but they're basically around $10 a gigajoule. And you recall that we pay for transportation fuels between $28 and $38 a gigajoule. So there's space here in Canada to perhaps use hydrogen as a transportation fuel if we can get everything aligned. And certainly other places in Quebec, they have the lowest cost in the Asia Pacific region. Quebec, certainly Canada is identified in British Columbia and et cetera as having the lowest cost hydro for hydrogen that could be made from hydrogen from electrolysis, essentially what we call green hydrogen. So green hydrogen is hydrogen that's made from electrolysis with low carbon electricity, whether it's hydro or wind or solar or nuclear. And blue is hydrogen is made from carbon-based fuels, typically natural gas, but also there's other carbon-based fuels that can be used to make hydrogen. For example, there's one here, Canadian coal plus carbon capture and storage is right here. When we actually did our own analysis based on numbers in Alberta and Canada, what I've done here in these three charts, on the left is show the cost of diesel. So this is everything in here is Canadian dollars per gigajoule, and the typical cost, wholesale cost pre-tax, is about 75 cents a liter or about $19 a gigajoule. That's right in here. If we wanted to make hydrogen from electricity, and we were looking at something a similar price, you notice that the biggest factor in determining the price of hydrogen from electricity is the price of electricity. And in Alberta, our electricity prices tend to be around, $40 to $80 a megawatt hour, or 4 to 8 cents a kilowatt hour. And this is fairly expensive. It's more expensive than the cost of diesel, the wholesale cost of diesel. In Quebec, where you can get, and in some provinces, even Ontario, in the middle of the night and things, where you might be able to get electricity at sort of 1 to 2 cents a kilowatt hour, or $10 to $20 a megawatt hour, it is possible to make cost competitive hydrogen. In Alberta and in places and other places across Canada, where you can also make hydrogen from blue hydrogen from natural gas. It's much lower slope here from the natural gas cost compared to the electricity costs. It's just the nature of the system. But steam methane reforming is what you do, and then carbon capture and storage adds additional price, more or less almost doubles the price of the conversion. But still, you can bring in hydrogen at about half the cost of diesel, and about 1/3 the cost of green hydrogen in an Alberta situation, not in Quebec, of course. One of the things about blue hydrogen is that as you increase the scale of its production, the costs decline. So in fact, these are actually at pretty large scale costs. But the bigger the scale, the bigger the hydrogen demand, the costs decline. One of the challenges on green hydrogen is that it's taken advantage of the fact that we already have a grid, and when electricity is in surplus, when it's really cheap, then we can make it into hydrogen and you can get these good prices. But one of the challenges that we have to think about as we move, if you want to move to a green hydrogen, which is really where we need to be in the longer term, is that as you get a larger demand for hydrogen, the price often increases because you have to build new infrastructure, you have to build new hydro dams, new nuclear power stations, or new wind turbines, etc., and the price can go up. What we've been looking at in a hydrogen economy is something that looks, a hydrogen energy system looks like this, where you got supply as the top half of this circle and demand as the bottom half. And so in the top half, you can see we've got a blue hydrogen, which is really you can make hydrogen from bitumen with carbon capture and storage, or even coal. You could do coal gasification, for example. You can make it from natural gas. That's where most of the hydrogen in Canada is made today. It's not made it's made for industrial thermochemical processes, but most of it is made from natural gas, virtually all of it. And you can also make it from biomass. Green hydrogen, you can take hydro, wind, solar, etc., make electricity, and then do electrolysis. You make it from nuclear power, for example. On the demand side, we see in terms of market shares of where the economics is best to move forward, is really what we see as the primary beachhead market, because of what we already pay for transportation fuels, is the transportation sector, either using hydrogen directly in internal combustion engines, we'll talk a little bit more about this, or actually using hydrogen, converting it to electricity, and having fuel cell electric vehicles, which is what the industry we're talking about is most interested in. But there are some barriers to doing that. So both of these have a role, though. We see this as the beachhead market. There are some niche markets over here as well, in terms of using hydrogen to decarbonize natural gas, to meet clean fuel standards, perhaps, or using hydrogen for steel making or for other industries that already want to make hydrogen. They're interested in the reductant, and they're able to pay a little higher price for it than they might pay for natural gas. So our approach, and what I'm going to do now is walk through the approach that we've been using to try to explore and build a hydrogen economy in Canada. Our analysis basically says, look, if we're going to start this, one of the places that it really could grow a hydrogen economy is in Alberta, where we have cheap natural gas, we have huge capacity for carbon capture and storage at relatively low cost, and we could get this off the ground perhaps in Alberta. So our focus has been on the diesel heavy freight market because, as I said before, diesel prices per unit of energy are higher than electricity or heat. We have very concentrated demand corridors. You know, if you actually look at where the major fueling stations are for diesel fuel, they're on the major highways and major corridors. And I'm talking about big trucks now. I'm not talking about diesel cars so much. We're talking about the big trucking centers. And we also is a very engaged sector. We've done a lot of interviews and talks with the sector, and the sector has actually been very interested in finding an alternative to diesel. And they have, I would say, many of them have EV envy. They've been looking at electric vehicles, and they like the idea of the torque and the power that electric provides. They are interested in something that doesn't have some of the drawbacks of weight, etc. So approach we started about 2 years ago is to work with Trimac and Bison and about 5 or 6 other companies as well. We ended up having to go with only 2 of the companies for issue of getting a regional focus on this. And we got them interested in coming in for a zero emission truck collaborations. Those of you might have heard Jessica Lof talk about this work a few weeks ago, so I'll say very little about it. But basically, we brought together Ballard to make the fuel cells, Dana to make electric axles. Freightliner has given us a couple trucks without engines that we can build. And Nordressa is a Montreal company that is an electric vehicle trucking company, and they're doing the integration of everything and building the trucks in Montreal. And this was $7.3 million from Emission Reduction Alberta to support a $15 million consortia. What this will do is that these trucks will be fueled in Edmonton, drive to Calgary, 320 kilometers away or so, drop off a load of 63 tons or so, and then pick up another load and bring it back. So that we only need 1 fueling station. We got a 700 round trip. The trucks are being designed and built in the next 16 months. Should be on the road in about 16, 17 months from now. And the hydrogen will be coming from hydrogen. We'd say no carbon management here. We're actually now negotiating with companies that can actually provide us blue hydrogen. That is where the carbon is managed. So we're excited about that. This is really a trial of the trucks, not so much a trial of the fueling system. So one of the approaches that we're doing in CESAR is with this hydrogen fuel cell trucking project, sort of launched, and it's going to be 3 years before we get the final results back from that. We basically, our focus is on how do we piggyback on that and build out supply and demand at scale and with coordination to actually create corridors of high hydrogen demand. So we're looking for a low cost feedstock. We want it has to be blue hydrogen, where we're not too far away from demand centers. There's no sense having a nice blue hydrogen source where 300 kilometers away from where anybody uses it. So we need supply and demand close together. We want to be able to have the potential for pipelines to come in because that can really reduce the cost of distribution hydrogen by an order of magnitude essentially. And so this is on the supply side. On the demand side, we're certainly interested in hydrogen fuel cell electric trucks. When they become commercially available, there's a number of trucking companies that are coming out that are making only hydrogen fuel cell electric trucks. They're not in Canada yet, and we're in discussion with them. And their big issue is that give us a hydrogen corridor and we'll be there. So we're trying to create the hydrogen corridor. So what we see is a big opportunity to create that corridor in this in-between time until we can get the corridor up and attract the hydrogen fuel cell vehicles. Is to put hydrogen blends with diesel in existing vehicles. So I want to say a little bit more about that. And we're also looking at opportunities to put hydrogen into natural gas pipelines even into power generation to decarbonize and meet fuel standards. And also looking at opportunities to put blue hydrogen into some of the industrial uses now, which a lot of hydrogen makes bitumen, ammonia, steel, methanol, etc. So one of the things we've been looking at is where in Canada, and specifically in Alberta, which is we can make the cheapest hydrogen and we can sequester it. And there is Edmonton's down here, if anybody knows the maps of Edmonton. Fort Saskatchewan is just a little bit up the river here, and then we have these airport around Scotford, and there's a bunch of refineries. This is all of a lot of the big industrial location here in Alberta, just northeast of Edmonton. And essentially here we have a hydrogen pipeline that already exists, which belongs to Air Products. We have a CO2 pipeline that is put in for doing enhanced oil recovery. We've got another CO2 pipeline here that does sequestration, injection of CO2. In this region, it is possible to make hydrogen and pay for all the sequestration of the CO2. This would be at the high end of the price. It's probably less than this, but at the maximum price, about $1.50 a kilogram of hydrogen, about $10 a gigajoule. It's, it could be less than that, could be $9 or $8 a gigajoule, but at $10 a gigajoule, it's even the economics should be able to work pretty well. We could put the CO2 in one of the CO2 pipelines, and the overall cost of the CO2 is somewhere between $35 and $55 per ton of CO2, with net across just making the hydrogen and letting the CO2 to go to the atmosphere. So this gets into the, as you know, we're heading to a price regime in carbon around $50 a ton of CO2. So we're within by 2022, 2023. So this is possible to do it, and we can make a net zero fuel from hydrogen. The real issue is where we're going to find the demand. So we've been looking in areas not too far away, ideally connected by a pipeline, where we can actually talk about putting demand in. So one of the places we looked at the end of that pipeline, and we got some data on the GPS tracking of all the trucks. In Alberta, all the trucks, as most part of Canada, every truck on the road has a GPS, and it pings up to a cell phone service about every 3 minutes of where its location is, and so we were able to get that data and terabytes worth of data, and look at a month's worth of data. This is 1 month worth of data in 2016, where we are looking at where the trucks are all. We got a ping for each truck. We can tell what company they belong to. We don't know what company they are, but we could figure that out pretty quickly when we went through the data and said, where is a truck parked for 15 minutes or more? So that get rid of all of the bings on the roads, and we only see where they park, right? And so you can see you got Trimac here, Karen. You can see the color coding is different companies. And you see this is a Flag J Truck Center, which is basically a Shell station at this location. And you see lots of different colors because they're in there refueling. So this allows us to get information on fueling centers and the possibility of, we're now talking to try to look at a short pipeline that would come into this region. And we're just in the process of trying to negotiate. We'll say, well, let's see if we can get a fueling center done that would be really low cost hydrogen, more sort of the hydrogen that most people in the hydrogen economy haven't thought we could get these prices until, say, 2035 or 2040. We think we can do it within a few years. One of the things we've been looking at is, in order to create demand, is really looking at technology. There's 3 technology providers we found in the world. There are more than this, but we've been talking to these 3. These are, and they do diesel vehicle retrofits. They don't have a lot of vehicles on the road because there's no infrastructure. And the idea is they can what you do is you'd store the hydrogen on these trucks. These are diesel trucks. You'd put on the back of the trucks, you'd put a few tanks with 350 bar hydrogen, similar to what you'd use in a hydrogen fuel cell, basically the same gas. And so we have the same fueling station and it's in the same trucking stops. You can provide 30 to 40% of the fuel energy from hydrogen. You actually get up to 70% or more, but the best results are at 30 to 40%. And the hydrogen costs, we think we could bring in the hydrogen costs lower than diesel. I'll show you some of that in a minute. The companies claim here, and we've been through the literature. I've been working with 2 researchers at the University of Alberta, very talented mechanical engineers that are actually been working on validating and reporting and improving on these technologies and verifying it to give the carriers confidence in that this is a credible technology. They claim they get even with a small amount of hydrogen, 10% or 5% hydrogen, you get about a 90% reduction in particulate emissions because hydrogen improves the combustion. And this has been verified by a lot of reports in the literature. They also claim to be able to get a 50% reduction in NOx. And we're that's one of the things that our researcher friends here are questioning and want to see. Well, I want to see the evidence of that, and they can certainly measure that. And they also get a 30-40% reduction in CO2 emissions because you're replacing 30-40% of the diesel fuel. And the beauty of this technology, it's relatively low risk for the carriers, because if they find out they're driving and they can't refuel, they're not near a hydrogen filling station, it's fine. It means their carbon emission goes back up, but they can at least run their vehicles and they're just back to a regular diesel vehicle. So it's not, it's a lower risk than hydrogen fuel cell electric. And what we're trying to do is to actually get the trucking companies engaged in a transition. We're talking about building transition pathways. So how do we build the infrastructure without having to actually make a multi-billion-dollar commitments to fueling stations or trucks without fueling stations or fueling stations without trucks? And the conversion costs, we're getting details. We're trying to nail these down. I don't want to give them out now, but we've got lots of meetings going on to try to figure out the pricing and what the business models would look like. One of the strategic roles for hydrogen diesel and biofuel trucks is they provide a potential for really rapid growth of hydrogen demand. And we can actually, this is a very simple technology. It is not a rocket science by any stretch of the imagination. It's just pressure tanks and a little computer controlled valve that squirts hydrogen into the engine right with the diesel, simple modification of the engine. This means we could go from, once we've done 10 trucks or something, we could go to hundreds and thousands and even tens of thousands of trucks potentially on major corridors and get a 30% reduction in that freight sector. But actually the real value is we create the infrastructure of the fueling stations, we demand for the blue hydrogen production, get the price down, we get the price of the vehicle retrofits down, we can justify putting pipelines in, we can justify vehicle storage tank, getting the price of those down, which are really not made enough quantity to be cost effective. And once the fueling stations are in place, there's really a potential to attract hydrogen fuel cell electric vehicles, OEM and fleet operators, the fleet vehicles, because there's a lot of companies competing in this space. The big barrier is getting the hydrogen corridors. The technology, we know the hydrogen fuel cell electric technology works. Having it work under Canadian conditions, -40 once in a while out here, is a question we really need to test. We'll be trying that out. But in the meantime, we can use the hydrogen and diesel paths. With government support, there's relatively low risk and some benefits for the freight sector, and we're putting together some suggestions on policy programs that could be used to implement this, and trying to generate credits under the clean fuel standards, which actually could really help with the economics. And the new clean fuel standards that is coming out this year or next year, and increased comfort of the industry working with hydrogen, which is, I think, a really important contribution as well. In terms of the cost, numbers are showing here. This is the carbon abatement cost tied to the price of diesel. So if you're paying $1 a liter for diesel, which I think maybe I should talk in Ontario time, $1.20 here, anything up to $4.50 a kilogram if you're in a hydrogen biofuel vehicles. At $1.20 a kilogram here, you could go probably $5.50, even $6 a kilogram. And you should be, the cost relative to, you could go up to that price and still it would be lower cost or at the same cost as diesel fuel. So anything in the green shaded area on these two charts should be attractive to carriers. The last approach, and before I finish, we'll maybe take some questions and discussion, is what we're really trying to do is we see this as number 2 here, you can see in the shading, is to really build supply and demand and really try to build out the system. But then it's really, how do we grow it? And we look at growing this supply and demand along the transportation corridors. As it turns out, our transportation corridors for freight is really the major highways across Canada. We should be able to grow it. This actually tends to be the same corridors where we have our pipelines. They tend to follow the road corridors and train corridors, and obviously the train lines, etc. So the scale. So what's critical here is the scale is critical to preserving the economics and attracting investment. And we really got, if we're going to reach net zero by 2050, we've got to think about major investments in transforming infrastructure. Our focus right now is to look at, going from 2 to 100 to thousands of trucks focusing on the Edmonton to Alberta corridor, we've been talking with the airports. We have an airport here in Calgary in the north side. Driving north, it's on the right-hand side. There's one here in Edmonton. The Edmonton International Airport is on the south side driving. We talked to the airlines about, replacing their ground vehicles with hydrogen. They're quite keen on that. If we can get them a hydrogen at a price. The hydrogen production centers are here and actually a lot all over Alberta. We probably make more hydrogen in Alberta than just about any place in Canada. We just don't capture the CO2 and store it, and we don't use the hydrogen for transportation. We use it for cracking bitumen and making fertilizer, etc. So what we're talking about is trying to build along these corridors, build at scale with the methods we've already talked about, and try to create fueling stations in the 2 to 10 tons of hydrogen per day. So if you're spending $4 a kilogram for a fuel and you got a 10-ton a hydrogen, 10-ton a day fueling station, the cash flow in that fueling station is in the $40,000 a day, and that's enough to pay for a significant amount of infrastructure, to pay for your fuel, and to pay for salaries, etc. So the issue is target the economics to get it so that we build out this energy system and it becomes self-sustaining once infrastructure is in place. We're doing this through pilots, demonstration, commercialization initiatives. We've got a number of these going. We've heard about one, AZETEC. We hope to have announcements about a lot more coming in the next year. We're also very interested in even discussions in Eastern Canada, but doing something similar in the Quebec to Detroit corridor. This is actually the largest heavy freight corridor in Canada. We see a huge opportunity here. Quebec is already in the process, very much in the process of making green hydrogen in significant quantities. They're actually talking about, liquid hydrogen in the range of 10 tons a day, and even more 20 tons or 30 tons a day production in Quebec. They've already done a call for proposals for fueling stations. Their focus has been in the past on smaller vehicle fueling stations. We're arguing strongly that they really need to think about trucking fueling stations, and we really need to be thinking about hydrogen going into as a diesel mix, fueling trucks to move up and down these corridors, and we can actually get the economics. We think the economics of that could be achieved much more rapidly, and once you have that, we can attract the hydrogen fuel cell trucks because you can get the prices down. The big opportunity we see is the Port of Montreal. A lot of container ships come in there and they unload to trucks, and the trucks coming in with container ships getting loaded up. You want to go to Mecca, if you like. You want to go to where the center of it is, and you can where we can get the biggest market share, because it's all about scale. We see this as an opportunity to really an energy system that works for all parts of Canada. There's some provinces where blue hydrogen makes, some where green hydrogen makes more sense. Some provinces like BC where both make sense depending on where you are. We see the anchor tenants are road freight, trains, fleet vehicles, hydrogen exports. We can talk a little bit more about that if you like. Even ships and planes eventually, decarbonizing natural gas eventually, but the economics is not so good there. We see these as being an opportunity of hydrogen, could be a way of bringing Canada, the various provinces and regions of Canada together with a shared vision. I hate to use the term national energy strategy or national energy program, but certainly a shared vision on a transition, what a transition to a low carbon and net zero Canada might look like. We also see an opportunity, and I'll just end with this, that we've talked about blue hydrogen, we've talked about green hydrogen, but actually where the real magic occurs is when they occur together in one jurisdiction. And we're doing quite a bit of work as we see blue hydrogen because of the cost benefit as an opportunity to use blue hydrogen to build out the infrastructure, to get the pipelines in place, to get the fueling stations in place, etc. But once they're in place, and they've got pipelines moving across areas where we have great wind or solar generation, there's a possibility for green hydrogen, for that to be wind and solar, to certainly feed electricity to the public grid and overbuild our wind and solar capacity so that there's excess, and put the excess through to make hydrogen, green hydrogen, possibly save the oxygen from that electrolysis of water, and then use perhaps natural gas, which is a really inexpensive source of energy, with oxygen, make oxy-fuel combined cycle, sequester the CO2, manage that, and then you can actually produce, when the wind's not blowing, the sun's not shining, you can produce electricity to the public grid. Either way, we see the evolution in the future of the future evolution of our energy system to a net zero, where these barriers between the three sectors of the energy system that we have today will be broken down. And we'll be talking about more of an integrated energy system where electricity is integrated with our fuel production and our transportation is integrated with our thermochemical needs. And maybe we have more of a one energy system, which is much more robust, much more, and has some real economic and environmental benefits. So that's all for the presentation. I'm very happy to enter into any questions or feedback that you might have. Thank you.
All right, thanks very much for that, David. We do have a couple of questions that have popped up, so I'm going to go through these before I go ahead and unmute the lines. I kind of suspect that this question or comment was kind of answered largely with your last slide here, but I'm just going to put it out there in case there's any additional sort of comments that you can make on it. So it seems, the question is, it seems to me that hydrogen from methane or any other fossil fuels with CCS is actually green. So I guess that's just kind of a comment, I'm wondering if you could kind of address that any further than you already have.
No, I think that's actually a good point, and it's certainly very low carbon. It's what we've been looking at. The economics we've been dealing with is a 90% carbon capture from the 90% of the carbon produced in the production of the hydrogen is captured and geologically stored. So you could call it green. The terminology blue and green is coming out of Europe, and it's actually starting to be very commonly used across in people talking about a hydrogen economy. And there is a difference, of course. You can make hydrogen. I mean, you can make hydrogen from electricity that where the electricity is very carbon intense, and it's quote not going to be very green. So in some ways, blue hydrogen could be lower carbon than quote electricity-based hydrogen. But so there is a problem of the terminology a bit. The way we've decided to use it is, and we haven't yet got a standard for what is the allowed carbon intensity of hydrogen to be called blue or green or whatever. And there are committees that have been put together in Europe that are trying to actually sit down and talk about this. My sense is those are details, and I think that the concept of blue hydrogen is really is to recognize that you can make hydrogen with very low greenhouse gas emissions. And we can use our fossil fuel resources in a way that, which really actually helps to bring, I would argue, bring provinces like Alberta and Saskatchewan and other provinces, even, Nova Scotia, into the, creating climate change solutions, rather than only seen as part of the problem. We're now can be a major part of the solution. So I'm not fussed about the color so much, but the color terminology is certainly something that is in the literature. And if we called it green, we'd get more hassle than just calling it blue.
We've got another.
David, it's Joe Hall here at 360. Just a follow-up to that. In terms of the storage of the carbon that's produced in the blue carbon process, what is the storage capacity and what happens to the carbon over time? I think a lot of people would like to sort of understand what that is.
Sure. Well, most of the storage, and there was a lot of work done in this about 10 to 12 years ago. Matter of fact, huge investments about carbon capture and storage in Western Canada when there was a thought of that we were running out of natural gas. That we were going to have to go back to coal-fired power generation or even go more investments in coal-fired power. And we we're going to have to use post-combustion capture and storage of coal-fired power. So the storage is really, the one that's probably the lowest cost is called enhanced oil recovery. And it's not really a storage, it's basically you take the CO2, you compress it and inject it into an oil well. It's at supercritical CO2. It actually mobilizes the oil. It sort of dissolves the oil effectively in the CO2 and helps to push it out of the well. But a significant proportion of the CO2 stays. You do get some of the CO2 coming back out with the oil, but most of the CO2 actually remains in the ground permanently. And that's being done in Weyburn, Saskatchewan right now. It's been done for years. It's being done in Alberta as well. And that's been around, there's, sort of 1 million tons a year of CO2 sequestered in Canada through that process. There's a limited availability of EOR reservoirs. And with the project we're talking about here, we're going to be, we would, if we went to a hydrogen economy, we would saturate those reservoirs and EOR reservoirs. And basically the CO2 is worth something where to put into EOR reservoir, it's probably worth something like $20 to $30 a ton of CO2 is the value of that you get back in enhanced oil recovery. The real long-term and major is a saline aquifer storage. And you can also put it into old abandoned gas wells and abandoned oil wells and store it there. The gas and oil were down there for hundreds of millions of years, and so we can just go back into those wells and put the carbon back in. And saline aquifer storage is one that's absolutely huge. And it's down, we're down 1.2 kilometers under the ground, maybe even 1.5, even 2 kilometers sometimes. And what you're doing is injecting it in, and it dissolves. This is a supercritical CO2. It's basically a liquid, and the CO2 goes in there, and it starts reacting with the rock. It reacts with the minerals in the rock, and over 100 years, a few hundred years, it actually turns to rock itself. But it's basically, capped and sequestered and monitored. So essentially, there have been studies done. The Quest project that I showed you a chart of is one that they're putting 1 million tons a year into sequestration sites, the 3 wells they have there, and they got a lot more capacity to put a lot more into those wells, and indeed are keen to use more of that capacity. So I think eventually there's thought about leakage from these wells. Most of the estimates that have been out is the leakage would be about 1% in 1,000 years. And so, essentially when you actually do the numbers on that, it's a very low leakage. But what it has to be done is you have to understand the geology. And in terms of capacity in Alberta, we've got a study. We've been talking with some people to get a study to update the analysis, but the analysis from 10 to 15 years ago was we could put 100 million tons a year of CO2 in the ground and do it for 100 years. So, and there would still be capacity left. So we don't see this as a permanent solution. Let's be honest. I think we eventually, as I said right at the start, we've got to go. We're going to have to figure out how we're going to do it. But it is a transition pathway. We're talking transition pathway the next 10 to 30 years. Then we're talking about transition pathways that are longer, that'll take us to where we ultimately need to go. And maybe we ultimately need to go is, we need another source of carbon-free. We don't have enough hydro dams we can't dam every river, and people complain about damming rivers for good reasons. So, we've got a limited hydro capacity. We've got a limited wind and solar. It's their intermittency. We could talk about nuclear at large scale. There's some problems with that as well, as everybody knows. We're not sure we have the final solution, but this will get us to a net zero economy. And I'm, having spent a lot of time looking at the studies from 10 years ago on CCS, I'm confident that we have the technology and the security to basically put the CO2 back in the ground where it came from, or the carbon back in the ground where it came from, and we can make it effectively permanently sequestered.
Okay, we got a couple more questions here. We've got another 11 minutes. So, as an option to biofuel diesel and hydrogen, did you look at compressed natural gas engines using hydrogen blended fuels in a single storage tank?
Actually, that's an interesting idea. The challenge, I guess the biggest challenge we had is we started this process by talking to the trucking companies, the heavy haulers. And these are the companies that are moving, and they feel they got burnt pretty bad by the movement to natural gas vehicles 10, 20 years ago or whatever it was. And they have tried out natural gas vehicles. They don't feel they have the performance characteristics. They had concerns with the maintenance and other things. One could argue that maybe some of those things have been solved, but when we're talking pulling 63 tons, 63-ton vehicles across, even when I talk to proponents of natural gas vehicles, they say, yeah, that's out of their class scale. And a lot of the freight across Canada, the heavy freight in Canada is in these big tandem trailers, these B trains with, 60 tons or more. And essentially, I don't think there's an interest there. I'd also say from a Transition Accelerator perspective, we are really looking at, we have 3 criteria for selecting and identifying transition pathways. It has to be credible pathways. It has to be so credible, technologically credible. We don't like Harry Potter science. So it has to be credible pathways. They have to be credible economically and credibly socially acceptable. Number 2 is they have to be compelling. They have to be compelling to the key stakeholders. They don't have to be compelling to everybody, because there's going to be winners and losers in the transition. But the key stakeholders, it really matters. And we would argue that the key stakeholders in the freight transportation sector are the freight companies that are moving the freight. They're the ones that have to buy the trucks. They're going to have the ones that run it. It has to be compelling to them, or we're not going to get there. And then the third, it has to be, and this is the one that I'm really focusing, we really spent a lot of time thinking about, it has to be capable of actually being on a transition pathway. We would argue that a lot of the government policies in the past that have been focused on incremental reductions in CO2 emissions. How many tons of CO2 you can get, percent, or how many percent emission reductions you can get. And what is incentivized is a whole lot of dead-end pathways, a whole lot of in putting in technologies that will, may reduce emissions by 10%, but are 20%. But you can't get above that without completely changing the system. And we would argue a transition, we consider it, you got to climb a very big mountain. A lot of our policies have incentivized, us to move and climb molehills. And the molehill's not connected to the mountain. And so we have to come back down in the valley and start all over again. And we would argue a transition pathway to net zero is we have to see it being on the transition pathway. And our focus, we would prefer not to have to go to hydrogen and diesel engines, but we see it as the most promising in our analysis after working on this for a few years, the most promising technology that will actually help us build out the hydrogen infrastructure. And once we have the hydrogen infrastructure, all sorts of things open up. The possibility of piggybacking on that infrastructure, pipelines I'm really talking about, built on the back of freight and heavy and other diesel uses like trains and even airplanes and fleet vehicles, that sort of thing. You can then pull a hydrogen line off and feed it to a steel plant, or even other sort of industrial facilities that need hydrogen for their processes, or even putting it into home heating systems, etc. Because it's the issue of how do you get there from here. And I would argue I've struggled many times trying to figure out how natural gas vehicles are really switching an infrastructure to natural gas vehicles is on a capable transition pathway. I think it's just, it's not really that much different than our diesel vehicles. So why don't we just, why replace it with hydrogen and lock us into a new infrastructure? I'd say we need to go to hydrogen, and we need to go with the ultimate goal of enabling hydrogen fuel cell technologies.
All right, thank you. There's 3 more questions here we've got on the chat, so I can just go through these here. So, is there any research on hydrogen from biomass? Example, hydrogen from anaerobic digesters.
Actually, it's not so much from anaerobic digesters. They tend to make methane. I think there is some interesting work, and there might be something on biomass that I haven't come across, but I certainly haven't seen anybody talking about doing it commercially. I think the exciting thing about the biomass and the opportunity is a gasification of biomass to make hydrogen, and then to basically capture and sequester the CO2. So that you essentially have as negative emissions hydrogen. And especially if we get into the $50 a ton, $60 a ton of CO2 range, or if you're near a CO2 pipeline, the opportunity, I think, for biomass to feed into a hydrogen system as well as into a CO2 into CO2 and get negative emissions is I think, the economics is increasingly compelling. The other possibility is you just do biomass to hydrogen and you let the CO2 go to the atmosphere. It'll essentially be the kind of a green, but we call it blue because it comes out of it's basically carbon based, but it would be essentially a low carbon hydrogen. And there's certainly you can search the literature, there's lots of papers on hydrogen from biomass that you can find.
Okay. As an option to, oh, sorry, I've already asked that one. Would hydrogen produced from the oil fields be lower carbon than from natural gas? For example, what the startup Proton Technology and other startups are doing.
That's a really good question. We've wanted to. I know Grant and the Proton Technology. We talk a lot, and I'm excited about their technology, and I think it's very interesting. One of the challenges that they're going to have is to be able to, they're going to need a full external documentation of what their carbon emissions actually are. And one of the challenges they have is their reservoirs that they're looking at are not down at the 1.5 to 2 kilometers. They're much closer to the surface. And so the CO2 that's created in the reservoir, they basically set a fire in the reservoir and heat it up and essentially convert through sort of water gas shift reaction. They produce hydrogen in the reservoir space and then tap off and pull the hydrogen out, leave the carbon behind. The trick is the carbon's as the CO2, it's not of a liquid because it's not deep enough. You'd only get a liquid about below 800 meters. And so there is an issue about how secure that CO2 is going to be. And whether it's whether it's going to come to the surface, and I think they got a lot of work going on to try to quantify it. My hope is it will work. It provides quite an exciting opportunity to produce it. It's certainly, from their numbers, it's less than half to 1/3 the cost that I just gave you. From when we talked about blue hydrogen at $10 a gigajoule, they're talking about doing it at $3 a gigajoule, actually at $1 a gigajoule, so really talking about it. So that would be a game changer if indeed the carbon was lower carbon. I worry a bit that the ability to, I want them to be able to demonstrate that they can actually do long-term, essentially permanent sequestration of that CO2 in the reservoir, and they haven't actually had a chance to do that yet.
Okay. I'm going to say we probably only have maybe time for this one more question, but we'll see how we do for time. So the question is, other parts of the world are dedicating to hydrogen. What would be needed for Canada to serve this export market on both the Atlantic and Pacific Oceans, and how lucrative do you think that might be?
Oh, I love that question. Just in downtown talking about that this morning. I think the exciting opportunity, we're talking about LNG exports from West Coast and East Coast of Canada. There's lots of talk about it and taking our natural gas resource and basically bringing it to the coast, putting it through a cryogenic process, essentially dropping the temperature of it so you convert the natural gas into liquid natural gas. That's about a minus 160 degrees Celsius. One possibility is that we could use exactly the same facilities, even the same pipeline, and put hydrogen into the pipeline, increase the hydrogen concentration in the pipeline, get it to the coast, and at minus 160, you get the LNG. You'd still have a gas in there if you had it mixed in the pipeline, and that would be hydrogen. You drop the hydrogen temperature, you chill it, you separate it from the gas phase and liquid phase, you drop the hydrogen temperature to minus 252, and now you got liquid hydrogen. The Japanese have already said they want to import 300,000 tons a year of liquid hydrogen by 2030. We've been talking about, what's the economics. They're willing to pay a lot more for that hydrogen. They're willing to pay for LNG, and that hydrogen that energy source would be carbon free. My feeling is it looks to be, from our analysis, highly lucrative if you put in the infrastructure. I would argue that, and I would certainly strongly encourage the companies that are looking at LNG terminals to rethink their engineering a bit. It's not, from our analysis, which I'm not an engineer that looks at this, but what I understand about the system, it wouldn't take huge changes in their system to make it LNG and LH2 terminals. And I think that the opportunity for Canada to export LNG and LH2 to the world from East Coast and West Coast is large and could be quite lucrative. We are, as I showed you the thing, one of the lowest cost places in the world to make hydrogen. And if the world's going to hydrogen, we can actually provide it. If we're smart, we can actually provide it to others at perhaps even a lower cost than they can make it themselves.
All right, so we have run out of time for today. We do have a few more questions on the docket, I understand, but we'll try to get to those just kind of on an offline basis. Just a heads up, just to kind of keep an eye out, we do have further seminars that we will be sending out some emails about in the coming days and weeks, so keep an eye out for those. I want to thank David very much for this presentation. It's been very enlightening. A lot of good information, I think, that we've been able to get from you. For everybody that's online, it is our intention to get this presentation. Today's presentation was recorded, so we will be making this available online to everybody at some point in the very near future on our website. Yes.
Thank you very much.
Again. Thank you very much. You as well.
Bye-bye.
Thanks, everybody.